Welcome to this next lecture. We were discussing a special form of the dispersion equation that describes flexural waves as a function of frequency. This is that special form. Okay, it has two main terms in it. This term that describes membrane energy related to membrane stresses, and this term that describes bending energy related to flexure caused by bending moments. Okay. Now, so Kz, what is Kz? Kz is the Kz. Okay. So I suppose the geometry is now Z in this direction. So pardon me. This happens in shells. People sometimes take this axis is x, so this axis is z, so this is now z. So the Kz, okay, it's not very disturbing. So this is now z axis. Okay, so we have z as the wave number, that is for the wave that is moving forward in the z direction, Kz. Okay, whereas n or n over a actually describes the wave number in the theta direction. Okay. So now we are going to look at both the wave numbers, the circumferential wave numbers, the circumferential wave number which is n over a, and the axial wave number Kz. Okay. Now, if we look at axial cutons, that means when Kz happens to be equal to 0 or the related lambda z happens to be infinity. Okay. What do we get? We substitute Kz equal to 0 in this. Okay. So what do we get? We get omega, let us say n square is equal to beta square n fourth into 1 minus a half 1 over 1 minus a nu 4 minus nu by n square minus 2 plus nu over n to the power fourth. Okay. So you can see that this becomes larger and larger for higher values of n. Okay. But approximately omega n square is beta square n fourth, or omega n is equal to beta n squared. Okay. So if I kind of say that omega n should be around 1, then I have 1 is equal to beta n square, okay, or n is equal to beta to the power minus half. Okay. So beta now, the parameter beta, which is h over a square root of 12, if it is smaller, okay, I can have more cutons, n goes up. Okay. So what are we trying to do? We are trying to look at the circumferential wave cut-ons. So, this is one type of circumferential wave which is breathing mode, the other was an oscillatory mode back and forth, the other was an oval mode. Okay. So, we are trying to look at what frequencies these cut on and propagate in the z direction, in the axial direction. So, in order to do that, we set kz to 0, that is the way you find out cut on frequencies. So, when we set kz to 0 in here, we get this particular equation which dominantly has this terminator, more accurate for higher values of n. Okay. So, if I kind of set omega n to be equal to 1, okay, then what that tells me is that if beta is very large, I do not have that many n below omega 1, whereas if beta is small, I have a reasonable number of n. So, that many circumferential patterns will propagate below omega, or start to propagate below omega equal to 1. Okay. So, let us get a feel for this number now. Okay. So, what we are trying to say is that, let us say this is kz axis, okay, and this is my omega axis. Okay. Then I have beta here, then I have 4 beta here, then I have 9 beta here, okay, then I have 16 beta here, and so forth. These are my cut on frequencies. Omega n is beta n square. These are my cut on frequencies with every n. Okay. So, the waves will cut on vertically, it will take off from the x axis vertically at these values. Below this value they will be imaginary. So, they are not cut on, they will be imaginary, but we are not interested in imaginary values, we are interested in real values. So, at these values you will have cut on of waves. Now, the question is, beyond cut on, what do they do? Beyond cut on, okay. So, I hope you follow. Let us say n equal to 0, then I have this breathing mode, okay. That means the shell breathes, its radius uniformly increases and decreases, and I am trying to see if this shape moves in the z direction or in the axial direction. Okay. So, this moves in the axial direction at all frequencies, it cuts on at 0 hertz, okay, or 0 frequency. Whereas, if I look at this ovaling mode, I have this basic radius shape and I have this ovaling. So, the cross section has an ovaling shape, okay. So, I want to know at what frequency this begins to propagate. So, here I put n equal to 2. So, at 4 beta, approximately at 4 beta. So, it takes off at 4 beta and starts to propagate. Propagate meaning what? It moves along the z axis, starts to move along the z axis. So, below 4 beta it does not propagate, okay, it is imaginary, it does not propagate, okay. So, that is what we are looking at, okay. So, now cut-ons we have looked at, but what about beyond cut-on, okay, what about beyond cut-on? So, beyond cutting on, how does it behave? Okay, the kz wave number, kz flexural wave number, or in terms of the basic number I said, K01 is flexural, So k11, so kn1 basically. Okay, so kn1 in terms of the 4 waves in the matrix. So we are just discussing flexure. Okay, and why flexure? Because that is what is capable of making sound in the medium. The others don't couple so well to the sound. Okay, the in plane axial longitudinal wave number or the torsion, they don't couple to sound so well. So we are interested in flexure. Okay, so this in the original notation it's k01, k11, kn1, whereas in the current notation we are talking kz, which is the flexural propagating wave number. So we know how the cut-ons are. Okay, so beyond cut-on what happens? So beyond cut-on we will look at the same dispersion equation, but we will ignore this less important term because we want to get a physical feel for it. Okay, we will ignore that term and look at how the dispersion equation behaves. So if I write that without that term, okay, so I have omega square given by 1 minus nu square kza whole fourth by kza to the power 2 plus n square whole squared plus beta squared kza whole squared plus n squared whole squared. Okay. Now I can further make all the wave number terms as kz beta to the power half or n beta to the power half. Okay. Okay. Now what we will do is we will keep omega constant, omega is a constant, and we will look at how kza beta to the power half behaves versus n beta to the power half. Okay. So let us look at this equation and make some judgments. Let us keep this equation in view. Beta to the power half is unimportant, but okay. So we will plot this later. So if omega is small, let us say, which means way less than 1, I suppose. Okay. Then we will call this term 1, we will call this whole thing T2. Okay. So these are all squares and positive numbers. Okay. So what that means is T1 plus T2 must be small, and so T1 must be small. Okay. So if for example the n term, n beta to the power half term is significant enough to account for omega square, that is what I mean. Okay. Then what happens is the kz term, the kza beta to the power half term has to be small. That is obvious. Okay. If n beta forms a substantial part of omega square, the kza beta has to be ignorable small value part of omega square, right. This is omega square. I want the total to be omega square. So that is one observation. Next, further, if omega again is small, the same value as above. Okay. Okay. Then of course T1 plus T2 must be small. Okay. But if n beta to the power half is a small quantity, is small. Okay. If k kz a beta to the power half is large, okay, now you can imagine what is going to happen. So n beta half term is small and kz a beta is large. Look at this term over here. This term of course will be large, okay, or substantial. What I mean is kz a is compensating for the n term within that, but if kz a is big, then this term approaches 1. Okay. So there may be no solution, because omega is finally small, or omega square is small. Okay. So in the event that the n beta term is small and kz a beta term is large, then what will happen is this first term will tend to become close to 1 and everything is positive again. So you may not be able to match omega square. Okay. Whereas if n beta term is small, okay, and kz a beta is adequately small, okay, then small plus small, this will acquire some value, whatever value it acquires. Okay. But here, because kz a fourth is there, it will be a small value, it will be a small fractional value. Okay. So T1 can be small also, T1 can be small also. So this T1 small plus T2 small having small terms, it is possible to find a solution that equals omega square. Okay. So this is very peculiar, right? You have two terms and there are values of omega where a component term n is small, then the other kz a also has to be small in order to equal. Okay. Now we shift the argument, if omega is large, if omega happens to be large, let us say in the range of 1 or greater than 1, okay, if now n beta half is big, okay, then kz a beta to the power half can be small, that way within T2 there is kz a which is small and n which is large, and here in the other term kz a beta is small in the numerator. Okay. So this term is small, the T1 is small. And T2 is adequate, so that the sum equals omega square. Okay. Further, on the other hand, again if omega is large again, and that means greater than or equal to 1, okay, and if n beta to the power half is small, okay, then kza beta to the power half can be big, okay. Why? Because n beta half is small but not 0, therefore T1 only approaches 1 from the lower side. So T1 is less than equal to 1 and T2 can be adequate such that together they equal omega square. These are just arguments. In actuality you have to plot and see, okay. So what does this mean? If we now plot this argument, the logic we have presented, if we plot it, okay. So this is my axis here. So I am going to plot n beta to the power half here along this axis, plot k z a beta to the power half on this axis, okay. And I am going to plot constant omega pictures, constant omega is constant. So let us say omega is 0.16, okay. So what will happen is, if n beta is large, kza beta can be small, but if n beta is small, then kza beta has to be small. This is omega 0.16, okay. Next we look at omega 0.36, let us say. This is the picture that emerges, okay. Omega 0.64, this is the picture that emerges. And this is the picture that emerges for omega equal to 1. And further omega equal to, let us say 1.44 whatever. So beyond omega equal to 1, the picture kind of becomes normal, okay, and T2 begins to take over, okay, where you have kza beta to the power half squared plus n beta to the power half squared. So if one is big, the other is small, if the other is big, this is small, the red lines tell you that. So T2 has become dominant, but below omega equal to 1, omega equal to 0.64 and so forth, okay. At lower values of n beta, you will have T1 dominant, okay. So T1, as I said, speaks of membrane energies or membrane stresses, okay. So then there is this region here where the membrane stresses dominate, okay. What is important? As a result of membrane stresses, at low frequencies, right, omega equal to 0.16, 0.36 etc., the flexural catons have low wave number values, kz values are low, that means wavelengths are large. wavelengths are large. Okay, so this wavelengths are large aspect we will this aspect relates to external radiation. Okay, external radiation. Why? Because for good radiator the wavelength on the structure must be bigger than the sound wavelength. Okay, so that is what, so external radiation lambda z is big, large. Okay, so this relates to external radiation, we will discuss that later. Okay, so now these kz's are low, that means they cut on. We have seen cut-ons before, right? Cut-ons we saw before, which where omega n is n beta to the power half. Okay, so just cut-ons we saw for various values. Now we are saying how they behave as a function of frequency. Okay, so how do they behave? If I take a value like this, if I take a straight line like this, okay, these pictures are for constant omegas, these pictures are for a single omega. Okay, but suppose I vary omega, as I move from small values to large values, somewhere close to omega 1 the wave number picture unwinds rapidly. Okay, if it is more dramatic here, I have low values of kZa, low values of kZ. Suddenly from here till here the kZa opens out rapidly by the time I reach omega equal to 1. This vertical line here is for a constant n and beyond, of course. Okay, so if I draw this particular picture, so now we draw a different picture. What is that picture we draw? So we have this omega equal to 1 value. So I have been saying that omega equal to 1 is an important number. This is the ring frequency. Okay, so now I have this flexural wave number, let us say n equal to 0, that cuts on at 0 frequency but remains low, right, as the picture showed, it remains low, but as I reach omega equal to 1 I rapidly change. Next is n equal to 1, which cuts on here and stays slow, and I approach omega equal to 1 rapidly like this. Maybe one more cut on starts off like this. Okay, stays low and then, okay. Now again in all of this, this is the region beyond omega 1 is the region where these wave numbers acquire dominant flexural behavior. But there is some flexural, these are dominantly longitudinal, but they do have flexural components in them, flexural components. Okay. Now let me just say it here that where does the acoustic wave number line sit? Acoustic wave number line. Okay. The acoustic wave number line can sit here in this manner, is possible. Okay. Or the acoustic wave number line can sit like this also, depending on the medium, etc., etc. Okay. Now we are going, so this is so far the structural picture, structural wave number, the structural okay, flexural, that's important, wave number picture. Okay. Just for you to have a feel, we said that the number n is equal to beta to the power minus half, okay, gives the number of modes that cut on below omega equal to 1. Okay. So, beta becomes smaller, you get more n. So, just to give you a feel, if h by a, which is related to beta, is 0.003, then we get n equal to about 17 modes, and if h by a is equal to 0.05, then we get about n equal to 4 below. Okay. So, this is the structural picture so far. Okay. We have to bring in the acoustic picture. Okay. We are talking of sound and structural vibration. For internal coupling, the cylindrical shell has fluid inside and we are going to discuss coupling. Okay. So far we have only presented how the flexural waves in the shell behave. So, we have to add the fluid picture. We will do that in the next class. Let me close this here. Thanks.